Hello again, everybody. We're going to talk about element symbols today, and we're also going to relate that to some of the concepts of subatomic particles and atomic structure. All kinds of good stuff is going to happen in this video. One thing I'd really recommend that you have available is the periodic table that I included as a resource guide, because the periodic table, keep in mind, is the ultimate cheat sheet in the universe. And it really helps to have one right in front of you to kind of make sense out of a lot of these concepts. So the first thing I gotta talk about is this idea that there's a couple of different parts of an element symbol and a couple of different rules. So let's just pick out kind of a random element. I just happen to pick out the element that is represented with a CO, which you should be able to find on the periodic table, which is cobalt. So here's an element, and so what we need to figure out is, what does this atom actually look like? Well, there's a couple of items of information that you'll find on the periodic table. But first we got to talk about the importance of not always writing with caps, right? Those of you that have ever gotten a text from people that just always have, they're always shouting in their text messages and stuff like that. Chemists kind of have a similar thing going on in that, like, capital letters are really only kind of kept for really important things. So it turns out in an element symbol, you're always going to have at least one capital letter, or only one capital letter, I should say. And if there is a second, not all of them will have a second letter, it must be lowercase. And so I'll just kind of show you an example of why that's important, right? Let's say I was writing in all caps and I was talking about cobalt. Well, it turns out that I have an element written right here, but as we start to talk a little bit more about this symbolic representation, it turns out that if I have two capitals together, that automatically means I have some sort of bonding situation, right? And so this thing, right, if we look it up on a periodic table, this is cobalt. And when we start talking about naming covalent compounds, you actually find out that this is called carbon monoxide, right? Two totally different things, in case you didn't know. So it's really important when we write our element symbols that we don't do that, all caps game. Okay, so well, we know that's cobalt, but there's not a ton of stuff that we can figure out from this particular element symbol in terms of what that atom actually looks like. So what I'm going to do is I'm going to draw just like a really simple representation of an atom in this available space over here. And so keep in mind, right, that we've got a certain atomic structure that must always be maintained. Number one, you start with a nucleus. Watch how I do my nucleus. Right? You can't even see that probably. That's because I know that nucleus is crazy small, but super dense, right? We got all the mass in that little tiny nucleus and no volume, right? And so to represent the volume, at least in this kind of like simple way of representing atoms, I'm going to, just put a big giant circle, and I'll just pretend, right, that out here I have a bunch of electrons. Okay, and you'll notice that I use like an E with a superscript minus. That's often the way that we represent either electrons or electricity and things like that. So let's take a look at this nucleus and figure out what the periodic table can tell us about cobalt and how many different subatomic particles that are contained in that thing. Well, if you take a look at the periodic table that I included, you'll notice that on that periodic table next to cobalt, there are two numbers. One is a 27, and the second one is a whole bunch of decimal points, right? It's some number with a whole bunch of decimal points. So those are two really important items of information. The 27 is probably, in my opinion, the most important one at this point, because it turns out that cobalt has to have exactly 27 protons. That's what that number corresponds to. So we can just kind of keep track of the subatomic particles. And we know already, just from those two letters written on the board, exactly how many protons I have. It turns out that I have exactly 27 protons, right? And that's the way that sucker looks. So, what else do we know? Well, it turns out that at least for this week, this will change next week, it turns out the number of protons are always equal to the number of electrons in an uncharged atom. That's pretty important. Everything that we see this week is always going to be uncharged, right? It's not positive, it's not negative, it's just overall neutrally charged atom. Turns out that we also can say that there are 27 electrons in there. So that's actually a bunch of information, so let's actually include that on our little model of the atom over here. And the way that I indicate usually protons, and the way you should if some jerk asks you about this on an exam, right? I put a little arrow and I say, hey, I know that there are 27 protons in there. And I also am going to include the charge, which is plus, right? Because we know the nucleus is always plus charged. And I'm going to take my electron count, and I could put 27 dots around here, but I don't want to do that. So what I'm going to do is I'm just going to say 27 electrons, right? And for now, for about the next period of this video, that's all we're going to worry about in terms of electrons. We're not going to worry about the fact that these things orbit in different subshells and levels and everything else. That's kind of for the next video to figure out. I mean, it's an important concept, but let's not try to figure out everything all at once, right? Let's understand this. So notice it's uncharged overall because I've got exactly the same number of negative charges as I have positive charges. One thing that'll change next week is once we start taking away or adding electrons, that results in a charge, right? And that's what's called an ion. And we talked a little bit in a previous video about anions and cations. That's where they come from, okay? So you should probably notice that there's, one major subatomic particle missing here. And so hopefully you know what that is. Say it with me. I don't hear anything. Even my dog's not yawning. Neutrons, right? Well, how the heck do we know how many neutrons are in this cobalt? And there's kind of two ways, really, that you can figure this out. Probably the way that is the most common is that I will talk about what's called a particular isotope of cobalt, and I'll indicate that with a number. And I'm just going to kind of pick one at random. I'm going to say that my cobalt is a cobalt 62, right? You'll hear that if you've ever heard anybody talk about nuclear chemistry and stuff like that. There's always some element name followed by a number, right? And it turns out that number is pretty important. That thing is what's called a mass number. All right, so that 62 corresponds to a mass number. Keep in mind, what are the two particles that make up the mass of an atom? Well, it turns out we've got protons and we've got neutrons, right? And so that number, that number that I kind of picked at random for this cobalt isotope, right? I'm talking about an atom of cobalt that has 27 protons. It has to because it's cobalt. And then the rest of that 62 is made up of neutrons, right? Our missing particle. So I kind of had to give you that extra bit of information about mass number in order for you to make that, that assignment. And so what we're going to do is we're going to take 62 and we're going to subtract 27, and oh man, this isn't a math class. Whew. Let's see if I can do this. By the way, in class I have a condition known as board brain, so hopefully it doesn't happen in video form here. So what we have is, assuming I did this math right, please check me, that we have exactly 35 neutrons in this sucker. All right, so let's kind of summarize that. We've got 35 neutrons. Well, I'm going to tell Sean that I know what the charge on a neutron is, right? It's neutral. So I'm going to put a little subscript 0 right there. And then just to kind of keep the rainbow coming here, let's put another arrow and say, okay, I know there's 27 protons in there and that I have exactly 35 neutrons. Okay, so in one of your supplemental lecture slides, it'll actually define mass number in words, but just keep in mind, right, that mass number accounts for all the mass of the atom. The only mass in the atom is from protons and neutrons, right? And so that mass number is always the number of protons plus the number of neutrons, right? Voila, we have all the information we need to kind of look at a cobalt atom. And one of the kind of weird things about a lot of the symbology that we use in chemistry is if you spend enough time with this stuff, you get in the group mind, man. You get in the group mind and you see this and you say, I know what that thing looks like, right? And so you see these numbers and symbols, and this is what appears in your mind, right? So it's kind of it's a groovy thing, man. Nobody says groovy anymore, I know. But you notice how much information is actually contained in here. So I'm going to talk about a couple of other things that you're going to see in a couple of element symbols here. So we know that one is a mass number, right? I'm just going to clean things up a little bit. I'm even going to erase all of this, right? And you'll notice that we have just the mass number and the element symbol. Well, it turns out there are a couple of other kind of vocabulary words associated with atomic structure that are incredibly confusing. There are 3 of them. They all sound exactly the same to the first time you hear them, and they mean totally different things, right? So this is mass number. An optional little thing that I could do on this cobalt, and it's optional because I already know information about this cobalt from the periodic table. It turns out that I can put this number down here, right, which corresponds to the number of protons. That's all it is. And so this guy is called an atomic number. Okay? So an atomic number is different from a mass number. Okay? And the good thing about the atomic number is if you have a periodic table and an element symbol, you always know what the atomic number is, right? It never changes, right? If I change that from a 27 to a 28, I think I'm going to a nickel, right? And so check me on that. I have a horrible memory. But if I added a proton, that would be a nickel. So it would make no sense to put a 28 there. So for that reason, you'll quite often leave the atomic number off, and it'll just look like this, right? It'll just say cobalt 62. So, you can include them if you want to. You don't necessarily have to. One thing that sometimes confuses students is that on the periodic table, so if I were to write this symbol, right? I know I just erased it, but I'll write it down again, right? And let's say I have a cobalt 27. Well, the fact is that when we actually make our own periodic table, right, that 27 can kind of end up anywhere, right? And so I think even on the periodic table I gave you, it might even be written above the number and things like that. So on a periodic table, sometimes, you might be a little confused. What the heck is the atomic number, right? Well, it turns out there's only one whole number written on there. The other thing has a decimal point, which we'll talk about in a second. So, and another thing to keep in mind is that all these elements are all listed off in, a periodic fashion, right? So hydrogen has 1 proton, helium has 2 protons, right? And so you'll notice that it kind of goes 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 as you kind of go on. So don't be confused if this 27 is somewhere else on your periodic table. This position down into the left, right? Chemists are extremely specific about what they require. If you write the element symbol, if you write the atomic number, it must be down and to the left. And then this mass number must be always up and to the left, right? Or superscripted or whatever you want to call it. One thing you'll often see, and this kind of appears occasionally on a couple of worksheets we're going to work through in a second, sometimes instead of showing the superscripted 62, you might say something like that, cobalt 62, or you might say cobalt-62. So that's still a mass number, but I'm going to really try hard to kind of write things in the proper way, so it'll actually look like that. Okay, so back to our cobalt 62 here. We have to talk about something called an isotope, right? And so again, this is defined in a couple of those lecture slides. I think it's the second lecture supplement. But this is a little bit more fun for me than just kind of talking over a PowerPoint presentation. Plus, you guys get to see my really awesome Hawaiian shirts. So that's, you're welcome. So what is an isotope? Well, it turns out that I'm talking about a cobalt-62 isotope here, right? And that cobalt-62, of course, has 27 protons, 35 neutrons, and 27 electrons. Well, it turns out I can do something a little bit tricky. Let's, instead of talking about a cobalt-62, let's get crazy and let's talk about another isotope of cobalt. Let's talk about a cobalt-60, right? Okay, well, how is a cobalt-60 different than a cobalt-62? Well, it's a cobalt, so it still has 27 protons, right? So what must have happened? Well, I lost 2 mass units and it's still cobalt. Wait a second, that must have meant that I lost some neutrons, right? And so this really odd thing is true in chemistry. We can actually end up with very different numbers of neutrons for different isotopes. In fact, that's the definition of an isotope, right? It's the same element with different numbers of neutrons. And it doesn't really change the chemical reaction or properties of this thing. It doesn't even change really the physical properties of this thing, right? So those neutrons, I always kind of thought, like, why the heck do we need neutrons in there? And that's a pretty complex answer, but I kind of think about them as glue for the nucleus, right? You got all these positive charges in there that really want to blow apart due to electrostatic repulsions. Well, it turns out there's something called a strong nuclear force and a weak nuclear force. I kind of think about the neutrons as kind of the glue that holds that thing together. Not the best way to describe it, but it's kind of like, well, this is going way back, but when I used to really like glue, right, when I was a little kid, and I would make these like macaroni pictures of like my mom and stuff, but I love glue, man. And so the problem is that I like glue so much that I ate it. I turned out fine, obviously. And so like there was nothing left for my picture, and right, I didn't have enough glue in the nucleus didn't have enough glue for the macaroni picture. In much the same way, if you don't have enough neutrons in the nucleus, turns out that leads to something called radioactivity, where your nucleus will actually just fall apart, right? That's the kind of the basis behind nuclear chemistry. So just a little bit of insight into that and my disturbed mind. In much the same way, all the glue that the kids that like to just use a bunch of glue, right? You can get to a point where there's too many neutrons, and then you have the same problem where their macaroni picture would fall apart. So you can also have that kind of radioactivity in the case of an atom. So anyway, blah, 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 right? So the only difference between these two isotopes is the number of neutrons, right? And I could easily calculate that just by taking that 60 and subtracting 27 for the mass of the protons, and I'd end up with my 33 neutrons, I hope. So at this point, we've discussed 2 of the 3 major atomic structure vocabulary definitions, right? We've got mass number, which we know is the mass of the protons plus the mass of the neutrons for a particular isotope. We've got atomic number, which is on the periodic table and is the whole number on the periodic table and is the number of protons in the nucleus. And so now we have to talk about what the heck is atomic mass, right? And so bear with me a little bit here. Atomic mass is actually totally different than the other 2 concepts, but it kind of involves at least one of those concepts. So what I've done here is I've just kind of chosen some random isotopes of cobalt, right? They're all cobalt. The only thing that's different about them is the number of neutrons, right? That's the definition of isotope. And if you look at the periodic table, you'll see that there's this number with a whole bunch of decimal points there, right? And it's kind of curious that it's kind of very close to these numbers right here, okay? And so this, right, this mass in atomic mass units is actually an average of all the naturally occurring isotope masses, right? And so if you kind of imagine, you're a miner for cobalt or cobalt oxide, or I don't know how it's in the ground, but you kind of dig it out, and if you were to kind of zoom in and look at each individual atom of cobalt in there, it turns out the more likely the most likely mass that you're going to get is right around this number, right? And so it turns out, I'm not a cobalt expert, but the math tells me that it's very likely that most of the that ore of natural sample has cobalt 59s, right? And maybe there's just a tiny teensy bit, just a little bit of cobalt 58 in there. And maybe there's even barely any cobalt 62, right? So if you were to kind of take all of those numbers, and there can be 10 and 20 different isotopes of an element. So we're just kind of keeping things a little bit simple here. It turns out that if your majority happens to have a mass number of 59, right, you're going to end up with an atomic mass that is kind of very close to that number right there. So this number is truly just that, right? Atomic mass, also sometimes called atomic weight, or molar mass is another thing that we're going to probably call this by. Sometimes chemists can't figure out what to call it. But the thing that is true is that this is always an average of all the different kind of weighted averages of the isotopes here, right? And I'm never going to have you actually calculate this, but it's kind of good to know. And you'll hopefully remember at the very beginning of this, I said there's kind of two ways to calculate the number of neutrons in something. So really the best way is for me to give you a mass number, right? I have to give you this number or some way to figure that number out, right? And then you do that subtraction from the number of protons to end up with your number of neutrons. Turns out there will be some times where you're not given any information about the mass. So generally what you do is you take the atomic mass, round that number to the closest mass, and just kind of call that a mass number, right? But that's kind of bad form. I'm going to really try hard to make sure that I give you the masses of these things.